In the vast cosmic theater of the universe, black holes are undoubtedly among the most intriguing phenomena, yet our understanding of these enigmatic cosmic entities remains limited. Depicted as insatiable devourers of all in their path in countless science fiction films, black holes have long captured our imaginations. However, in a groundbreaking development, scientists have achieved a remarkable feat. They have peered into the inner workings of a black hole. This unprecedented endeavor raises essential questions about the true nature of these cosmic giants and challenges the fearsome depictions that have dominated popular culture. In this groundbreaking exploration, we journey into the depths of a black hole, shedding light on the mysteries concealed within its gravitational grasp. The mysteries of black holes. Unveiled. Black holes have a natural sense of mystery, making us feel like they are an incredibly deep and captivating force. Within this mysterious space, time behaves in a very puzzling way, which even the brightest minds struggle to understand fully as they try to figure out its confusing features. This begs the question, what precisely constitutes a black hole, and what confers upon this seemingly inconspicuous void its profound significance and immense power? The brief answer lies in the omnipresent force of gravity, and this gravitational pull renders black holes so profoundly influential. However, the more intricate and captivating answer delves deeper into the phenomenon. Black holes originate when the remnants of deceased stars, known as stellar cores, undergo cataclysmic collisions. When the accumulated mass surpasses approximately 3 times that of the Sun, gravity reigns supreme, overpowering all other forces. This overwhelming gravitational force compels the remnant to collapse in on itself, resulting in the creation of a black hole. These enigmatic cosmic entities are characterized by an extraordinary density, possessing such immense mass that their gravitational pull is so overwhelming that even light cannot escape its clutches. The majority of spiral and elliptical galaxies, as per astronomers' beliefs, harbor black holes at their core. There exist 3 distinct categories of black holes. The first category comprises stellar mass black holes, which are the smallest in size, typically weighing between 1 and 100 times the mass of the Sun. These black holes emerge from the collapse of the core of a massive star, often accompanied by a supernova or a stellar explosion. On the other end of the spectrum, supermassive black holes reign supreme, boasting masses reaching millions, if not billions, of times that of our Sun. These behemoths are thought to have attained their colossal dimensions through mergers with other black holes and the assimilation of surrounding stars. Intermediate mass black holes constitute a third category, inhabiting the space between their stellar and supermassive counterparts. Although relatively scarce in number, with only a few confirmed discoveries, these black holes are estimated to possess masses ranging from 100 to 100,000 times that of the Sun. It is believed that these intermediate mass black holes serve as the building blocks for the eventual formation of supermassive black holes through mergers and accretion processes. Beyond their role in elucidating the seemingly erratic motions of certain stars and contributing to our comprehension of galactic structures, black holes herald an uncharted realm of physics for the scientific community. They challenge existing paradigms and beckon researchers to embark on a journey of discovery and understanding in this enigmatic corner of the cosmos. The cosmic crucible of Einstein and quantum mechanics. In accordance with Albert Einstein's groundbreaking theory of general relativity, we delve into the fascinating phenomenon where matter exerts its influence on the fabric of space-time, ultimately giving rise to the force we know as gravity. Black holes, these enigmatic cosmic entities, emerge as dense celestial conglomerations of matter, boasting an extraordinary gravitational pull. However, the true marvel lies in the scrutiny of the black hole's singularity, where the forces at play reach staggering magnitudes, leaving the scientific community in profound contemplation. Einstein's general theory of relativity posits that as matter succumbs to the gravitational embrace of a black hole, its informational essence faces obliteration. In contrast, the tenets of quantum mechanics vehemently challenge this notion, asserting that such annihilation cannot transpire. Intriguingly, black holes emerge as a veritable crucible for astrophysicists and mathematicians, offering a fertile ground for the harmonization of these 2 divergent theories. Black holes, in essence, extend an inviting playground for experts in these fields, serving as a rigorous testing arena wherein the fundamental principles governing the cosmos can be scrutinized. The gravitational titans. There exists a prevalent misconception regarding black holes, one often characterized by the erroneous imagery of a literal hole in space. However, this notion is far from accurate. Black holes can more aptly be likened to supermagnets of cosmic proportions, distinguished by their extraordinary gravitational forces, which possess an unparalleled ability to attract matter. In essence, gravity serves as the underlying force responsible for keeping us grounded on Earth, preventing our untethered ascent into the abyss of space whenever we leap skyward. It is imperative to understand that the gravity exerted by Earth consistently pulls objects towards its center, only ceasing to do so once they reach its surface. Conversely, black holes wield gravitational forces of staggering potency, far surpassing Earth's comparatively feeble grasp. What sets them apart is their stark absence of a discernible surface to halt one's inexorable descent, thereby engendering the impression of falling into an inescapable chasm, hence the term black hole. The genesis of a black hole traces back to the dramatic collapse of a massive star, culminating in the formation of an entity of remarkable density. Within this enigmatic cosmic entity, an entire star's worth of matter becomes compressed into a minuscule volume. This accumulation of mass inherently begets an escalating gravitational influence. As the adage goes, mass begets gravity. In simpler terms, the more mass an object possesses, the greater the gravitational force it wields. This principle underscores the reciprocity between Earth and its inhabitants, where both mutually exert gravitational attraction on one another. Nonetheless, it is crucial to note that the strength of an individual's gravitational pull is intrinsically linked to their mass or weight. In stark contrast to a celestial body like Earth, the human body possesses a significantly weaker gravitational influence. This explains the peculiar phenomenon wherein astronauts on the Moon appear to weigh less. This observation arises from the Moon's reduced mass in comparison to Earth, which translates into a diminished gravitational pull on its surface, thereby conferring a perception of reduced weight to objects and individuals present there. The mind-boggling physics of black hole compression. The compressibility of black holes remains a truly mind-boggling concept. It is astonishing that a star with a mass equal to our Sun can collapse into a black hole that is merely the size of a small city. This extreme density is difficult to comprehend. To provide some perspective, consider the fact that the diameter of the Sun measures roughly 1.4 million kilometers, while a small city may span only about 10 kilometers in length. Thus, the compression of an entire star into such a diminutive volume is a truly significant reduction. This highlights the fact that referring to black holes as holes is only accurate in terms of the profound effects they have on their surroundings, not in terms of their actual nature. As one delves deeper into the topic, it becomes abundantly clear that black holes are remarkably complex entities. So if black holes are not mere holes, then what exactly are they? From a technical standpoint, black holes can be described as spheres, volumes of space taking on a spherical shape. They consist of two main components, the singularity at the center and the hypothetical border commonly referred to as the event horizon. The singularity represents a point of virtually infinite density without any volume. It exerts an irresistible gravitational pull, hence being the defining essence of black holes and the reason behind their distinctive properties. The singularity at the center of a black hole is incredibly small and dense. To illustrate, let's imagine standing on the North Pole. The gravitational pull in the northern hemisphere would be stronger than in the southern hemisphere because gravity varies with distance. This means we don't experience Earth's gravity equally at all times. The parts of Earth closest to us have a stronger pull, while those farther away have less pull. However, if all of Earth's mass were compressed into a smaller volume, gravity would become stronger. It's important to note that the mass remains the same. What changes is the density. Higher density means more concentrated mass and stronger gravity. This understanding of black holes and gravity reveals their fascinating nature. They challenge our understanding of space, time, and the laws of physics, and continue to be a subject of exploration and research in this captivating field. Unveiling the event horizon. In movies and illustrations, the event horizon is often depicted as a dark circle in space, encapsulating what we typically imagine as a black hole. It serves as a perimeter around the center, also referred to as a point of no return. Once crossed, anything that enters the event horizon is instantaneously pulled toward the center, with no possibility of escape. Although the event horizon may appear like a solid border or edge, it is in fact not physically tangible and contains nothing within it. It is important to understand that black holes are not technically objects in the conventional sense, since they consist primarily of vast vacuums. The singularity, located at the center of a black hole, holds all the matter, while the rest of the space surrounding it is essentially empty nothingness, giving the appearance of deep blackness. Any matter or energy that enters the black hole falls toward the center and merges with the singularity within a fraction of a second. The gravitational pull exerted by black holes is incredibly powerful. Its strength is such that even light cannot escape, rendering black holes invisible to direct observation. Therefore, instead of traditional telescopes, scientists rely on the use of massive radio telescopes and gravitational wave detectors to indirectly detect and study these mysterious cosmic phenomena. The triumph of gravitational wave detection. In 1915, Albert Einstein proposed a groundbreaking concept that objects moving through space can create ripples in the fabric of space-time, effectively merging the notions of space and time. This phenomenon can be likened to the way ripples spread across the surface of a pond. Fast forward to a century later, when researchers at the Laser Interferometer Gravitational Wave Observatory made a monumental discovery by directly observing gravitational waves for the first time. This remarkable achievement was a result of the collision between two black holes that occurred 1.3 billion years ago. One can identify the presence of black holes by observing their effects on the surrounding environment, particularly through their ability to draw in and superheat gas, dust, and stars. As these materials are pulled in, they emit radiation that can be detected as heat signatures. In April 2019, the Event Horizon Telescope, comprised of an array of 8 ground-based radio telescopes specifically designed to capture images of black holes, successfully captured the first-ever image of a black hole and its shadow. The target of this groundbreaking image was the black hole located in the galaxy Messier 87, part of the Virgo galaxy cluster. The captured image depicts a bright ring encircling the black hole, situated approximately 55 million light-years away from Earth and boasting a mass 6.5 billion times that of our Sun. This luminous ring, known as the halo, represents the intense heat emitted by hot gas swirling around the event horizon, the outermost edge of the black hole, before being inexorably drawn in. What happens when you fall into a black hole? When contemplating what would happen if one were to fall into a black hole, it becomes clear that such an experience would be far from desirable. No matter which type of black hole one encounters, the prognosis is quite grim. If, hypothetically, someone was to take the daring leap into a stellar mass black hole before anyone could intervene, their body would undergo a disturbing process known as spaghettification. Despite its comical name, the reality is anything but amusing. The immense gravitational force of a black hole would compress the individual from head to toe while simultaneously stretching them, resulting in a shape resembling spaghetti. Opting for a supermassive black hole does offer a slightly less horrifying outcome, relatively speaking. Let us imagine, perhaps for the sake of scientific exploration or to make an extraordinary leap for humanity, that one chooses to jump into Sagittarius A, a supermassive black hole located at the center of the Milky Way. Estimated to be approximately 44 million kilometers across and containing 4.31 million times the mass of our Sun, Sagittarius A was discovered by astronomers Bruce Bellick and Robert L. Brown in 1974 and subsequently named in 1982. The journey into Sagittarius A** begins once the individual crosses the event horizon, the point of no return. From the inside, one could still glimpse the outside, but no external observer would be able to see them. Any light emitted from inside would be captured and redirected back, preventing visibility. The comforting news is that although the gravitational pull within such massive black holes is significantly stronger, the stretching tidal force is comparatively lower, reducing the risk of being stretched into spaghetti-like strands. However, it is important to emphasize that these scenarios are purely hypothetical, as the extreme nature of black holes makes direct observation and exploration impossible. Nonetheless, the study of black holes continues to captivate scientists and deepen our understanding of the complex workings of our universe. Now, brace yourself for some rather disheartening news. Escaping from a black hole is an exceedingly challenging feat, if not impossible. However, there is a glimmer of hope in the form of the white hole theory. In simple terms, while black holes pull matter inwards, white holes expel it, though their exact nature remains enigmatic. Thankfully, there are tunnels called wormholes that connect black holes and white holes. Wormholes suggest that it might be possible to travel from a black hole to a white hole. However, this process would take billions of years. It's important to remember that this is still a theory being researched and refined, so we shouldn't get our hopes up or take any risks based solely on this theory. While the idea of white holes and wormholes is interesting and offers possibilities for space travel, it is still speculative and needs more scientific exploration and development. Resisting the gravitational abyss. Let us delve into the intriguing realm within a black hole and explore the consequences of being ensnared within its gravitational grip. Within this confinement, one may significantly contribute to the corpus of human knowledge by conducting a series of experiments. These endeavors might unveil a departure from the conventional belief that matter undergoes an infinite compression to a singular point deep within a black hole. Instead, a plausible alternative emerges: the notion of a Planck star, a theoretical construct postulated by loop quantum gravity. It is worth noting that loop quantum gravity itself resides within the realm of speculative scientific proposals, aiming to construct a quantum framework for understanding the fundamental force of gravity. In this framework, the fabric of space-time becomes quantized, comprising discrete units or chunks. These units, however, operate at a minuscule scale that renders our macroscopic movements seemingly continuous and fluid. The theoretical granularity of space-time yields two crucial benefits. Firstly, it provides a coherent explanation for gravity within the quantum mechanical framework. Secondly, it prevents the formation of gravitational singularities within the core of black holes. As matter succumbs to the relentless gravitational pull and undergoes compression within a collapsing star, it encounters resistance owing to the discrete nature of space-time. This resistance effectively curtails matter's journey beyond the Planck length, approximately 1.68 times 10 to the power of minus 35 meters. Consequently, everything that has descended into the abyss of a black hole is condensed into a compact entity, albeit not infinitesimally small. This resistance to further compression ultimately reverses the collapse, using a gentler term than explosion. Consequently, black holes reveal themselves as transient entities, destined for a finite existence. However, due to the extreme time dilation effects experienced in the vicinity of black holes, their demise unfolds over billions, if not trillions of years, when viewed from the perspective of the external universe. Gravistars and the Singularity problem. The concept of a gravistar represents a novel endeavor aimed at resolving the enigmatic singularity problem without relying on untested theories of quantum gravity. Despite its seemingly makeshift nomenclature, astronomy occasionally encounters such naming conventions. However, it is imperative to discern the fundamental contrast between a black hole and a gravitar. The latter is characterized by the presence of dark energy as opposed to a singularity. Dark energy constitutes a pervasive cosmic entity that permeates both space and time, inducing an outward expansion effect. While this might appear to belong in the realm of science fiction, it is, in fact, an established reality. Currently, dark energy is actively driving the accelerated expansion of our universe on a cosmic scale. In the context of gravistars, when matter falls onto them, it encounters a formidable barrier in the form of the interior's dense dark energy, preventing penetration beyond the surface. This is in stark contrast to black holes, which feature an event horizon. A crucial delineation points beyond which nothing, not even light, can escape. Recent observations conducted by gravitational wave detectors, such as LIGO and Virgo during the merger of black holes, have potentially discredited the existence of Gravistars. The rationale behind this lies in the distinctive signals that merging Gravistars would generate, differing from the signatures produced by merging black holes. These detectors are consistently accumulating new instances, further raising doubts about the viability of Gravistars. It is important to clarify that Gravistars are not explicitly prohibited within our universe's framework, but their theoretical foundation remains on precarious footing, subject to ongoing scrutiny and evaluation. Exploring ring singularities and wormholes. Planck stars and Gravistars, while intriguingly named, are not the sole contenders in the quest to comprehend the enigmatic phenomenon of a singularity's existence. Researchers have proffered an alternative, grounded in a more sophisticated understanding of black holes, one that departs from the notion of a single point of infinite density. This concept originates from our comprehension of non-rotating, uncharged black holes, which, it must be admitted, are somewhat unexciting. Authentic black holes, however, exhibit captivating behaviors, particularly when they possess angular momentum. A spinning black hole's rotation elongates the singularity into a ring-like structure, as stipulated by Einstein's general theory of relativity. Transitioning through this singularity's ring bestows access to a wormhole, and subsequently, an emergence through a white hole into an entirely novel and exhilarating cosmic realm. A challenge arises from the inherent instability of the interiors of rotating black holes, a consequence of the rapid rotation. This instability spawns considerable centrifugal forces akin to anti-gravity, which push rather than pull. As a consequence, an inner horizon forms within the black hole. In this region, radiation originating from outside the black hole is compelled by extreme gravitational forces to plummet inward toward the singularity. Paradoxically, the radiation encounters anti-gravity effects near the ring singularity, driven by the centrifugal forces. The inner horizon serves as a pivotal demarcation point. Any encounter with it would expose one to a barrage of infinitely energetic radiation, a condensed compendium of the universe's history, delivered in the blink of an eye. Now, it's time for today's subscriber pick. Now, let's delve into today's topic. The observation of a black hole consuming celestial objects is truly a magnificent spectacle. Recently, astronomers were astounded when a previously undiscovered black hole made its presence known by tearing apart and devouring a star that had ventured too close. This event occurred within a dwarf galaxy, located 1 million light-years away, and it is commonly referred to as a tidal disruption event. The TDE became visible to astronomers when it emitted an incredibly intense burst of radiation, briefly outshining every star within its dwarf galaxy. This remarkable occurrence presents an opportunity for scientists to enhance their understanding of the intricate connection between galaxies and the black holes that inhabit them. Additionally, it grants astronomers another intermediate black hole to scrutinize. This groundbreaking discovery has generated widespread interest because it enables scientists not only to discover more intermediate mass black holes within calm dwarf galaxies, but also to accurately determine their masses. This newfound knowledge holds great significance and promises to contribute to the advancement of our understanding of the cosmos. Let us know what you think about this discovery. Rotating black holes and mathematical precision. The emergence of an inner horizon marks the initial phase in the development of black holes. Nevertheless, the existence of rotating black holes within our universe poses a significant challenge to the accuracy of our mathematical formulations, hinting at the presence of peculiar phenomena. Fortunately, the advent of a groundbreaking concept called gravitational waves has provided us with our inaugural glimpse into the enigmatic interiors of black holes. This recent research endeavor holds the potential to greatly enhance our comprehension of the cataclysmic events that unfold when these cosmic entities collide, an occurrence that ranks among the most extraordinary and dramatic phenomena in the cosmos. In 2015, scientists achieved a historic milestone by detecting gravitational waves for the first time. This achievement was realized through the utilization of intricate and monumental instrumentation designed to monitor perturbations in the fabric of space-time generated by the collision of black holes. The consequences of this collision cascade throughout the universe, akin to the ripples created when shaking a sealed container and deciphering its contents by analyzing the resultant sounds. In the case of gravitational waves, the shaking stems from the collision of two black holes and the sounds emanating from the study of these gravitational waves. Subsequently, scientists have leveraged these measurements to refine their models of celestial occurrences, facilitating a deeper understanding of the internal structures at play and enabling the scrutiny of the validity of Einstein's theory of general relativity in extreme cosmic environments. As a result of these advancements, we are poised to embark on a journey toward unraveling the mysteries hidden within the heart of black holes. A quantum leap in scientific predictions. Until recently, scientific models primarily employed linear interactions as the basis of their predictions. While these models have proven effective, they possess inherent limitations as they do not encompass other types of behaviors that can occur in complex systems. However, emerging research on nonlinear interactions presents an exciting prospect for enhancing these models, potentially improving their accuracy by up to 10%. This development holds immense promise, particularly for the detection of colliding black holes, as it can enable scientists to identify and study such events with greater precision and confidence in the future. Advancements in understanding nonlinear interactions represent a significant leap forward in our quest to unravel the mysteries of the universe. By incorporating these new insights into gravitational wave detection techniques, we bring ourselves closer to the next phase of exploration. This progression holds the potential to deepen our comprehension of gravity itself and the awe-inspiring phenomena unfolding in the vast realms of the cosmos. The hidden secrets of holographic duality. Due to the impact of the pandemic, the Laser Interferometer Gravitational Wave Observatory, which made groundbreaking discoveries in gravitational wave detection, has been offline since 2020. However, there are plans to activate new systems in the coming years that may enable the detection and study of black holes with greater detail. Black holes have fascinated scientists for their profound mysteries, and a recent study from the University of Michigan has added another layer to this intrigue. The study suggests that black holes may be akin to holographs, although it is important to note that the researchers are not suggesting black holes are like the holograms commonly depicted in science fiction as mere projections. Instead, they are using the concept of holography to explore the connection between the inside and outside of a black hole. Led by Enrico Rinaldi, the research is based on the principle of holographic duality. This principle posits that the theories of gravity and particles are mathematically equivalent. Gravity theory describes the third dimension, while particle theory accounts for the second dimension. Both theories play a crucial role in understanding the functioning of black holes. The study delves into what this holographic duality concept means for black holes and seeks to uncover the secrets held within them. A three-dimensional perspective. Our comprehension of the inner workings of a black hole heavily relies on gravitational theory. According to this theory, black holes operate in the third dimension, where space-time flows into and through them. However, it's important to note that the calculation of the external aspects of a black hole differs from how we understand its interior. Despite the fact that the inside of a black hole operates within three dimensions, the exterior is perceived as flat. Ronaldo's recent research employs a simultaneous utilization of two simulation methods to calculate and elucidate the gravitational properties of a black hole. The immense gravitational force within a black hole is so overpowering that it remains imperceptible to the human eye. Consequently, we must resort to mathematical models to comprehend the phenomena occurring inside. As Ronaldo suggests, the most suitable representation of what transpires within a black hole is akin to a holographic projection. In this context, a hologram serves as a 2D representation that conveys a 3D image. To illustrate, imagine a hologram of Tupac, but in 3D. It was displayed on a flat surface. Even though it was 2D, people could still see it as if it were in 3D. Scientists have also made a model of a black hole with a 3D center. They did this by projecting data from particles onto a 2D framework using quantum matrix models. The goal of this research is to study the relationship between gravitational theory and particle theory. However, it's important to note that the inside of a black hole is currently just a mathematical idea based on these calculations. We don't know for sure if our understanding is complete or if there's more to discover. We need to find a way to observe the inside of a black hole to truly understand the universe's nature. The TDE flare and the secrets of black hole masses. The TDE flare, identified in 2020, was initially detected by astronomers utilizing the Young Supernova Experiment, an astronomical survey specifically designed to spot transient cosmic events like supernova explosions. The early observation of the black hole beginning to consume the star was crucial in enabling an international team led by scientists from the University of California, Santa Cruz, and Niels Bohr Institute, including astronomer Charlotte Angus, to accurately measure the mass of the black hole. The team found that the mass of the black hole falls within the range of 100,000 to 1 million times the mass of our Sun. Previously, TDEs have been successfully employed to gauge the masses of massive supermassive black holes. However, this is the first instance where they have been proven effective in determining the masses of smaller to mid-sized intermediate black holes. Consequently, the initial detection of the remarkably rapid flare serves as a reference point for future measurements of mid-sized black hole masses. By capturing this mid-sized black hole in the act of devouring a star, we were able to unveil what would have otherwise remained hidden. Flares from these black holes provide important clues about intermediate black holes, which might make up most of the black holes at galaxy centers. Scientists think supermassive black holes, much bigger than the Sun, could be formed by smaller intermediate black holes merging. Early on, the universe had small galaxies with these intermediate black holes. When these galaxies combined or were taken in by larger ones, their black holes merged, growing bigger. This process repeated, forming the huge, supermassive black holes now in most galaxies. A big question is whether all small galaxies have their intermediate black holes. Black holes are hard to see because they trap light, only becoming visible when they're actively consuming matter or disrupting stars. Are you more fascinated by the concept of black holes as massive gravitational traps or as potential gateways to other dimensions? Share your opinion in the comments below. Thanks for watching, and we'll see you in the next one.